Hello everyone. Today I would be giving you an overview on the topic iron carbide diagram. So before we jump into the topic, let's have a look at the cooling curve of pure iron. So this is called as the cooling curve of pure iron, and on our y-axis we have our temperature in degrees Celsius, and on the x-axis we have our reference with time. So above 1538 degrees Celsius, we've got iron in our liquid state, and these are the different regions which indicate different phases of iron. So between 1394 and 1538, we have a delta iron, which is non-magnetic in nature, and the structure is body center cubic. Between 910 degrees and 1394 degrees, we have our gamma iron, which is also called as austenite. This is again non-magnetic in nature, and the structure is face center cubic. And below 910 degrees and 765 degrees, we have our alpha iron, which is non-magnetic BCC in structure. Alpha iron is also known as ferrite again. And below 765 degrees, we have alpha iron again, but it is magnetic in nature and the crystal structure remains the same. One key observation what we need to know is that iron behaves magnetic in nature up till 765 degrees only, and post that it behaves as a non-magnetic substance. So this is about the cooling curve of pure iron, and one thing what we need to know is we need to remember the temperature ranges between we have different forms of iron. That is, we have our alpha iron, ferrite, gamma iron and delta iron in different regions. So identification of these things is important. Coming to the next part, we'll actually try to understand what an iron carbide diagram is and why is it actually necessary. So this is how uh, a typical iron carbide diagram looks like. But key points to note before going into this diagram is that it is actually not a true equilibrium diagram as what people say, because when I talk about equilibrium diagram states that the phases shouldn't change with respect to time. But if you have a look at iron carbide diagram, Fe3C, that is iron carbide, decomposes into iron and carbon, typically graphite, over a period of time. As in, like, let's say at 1300 degrees Fahrenheit, iron carbide, it decomposes into iron and graphite, but it takes a lot of time. So hence we are just considering it as an equilibrium diagram, but technically it isn't. Also, the iron carbide diagram, what you're seeing here, is just a part of the iron carbon diagram. It is not the entire iron carbon diagram. So these are a few things what you need to keep in mind before going into this diagram. So this is the list of points what I just told. You can have a look at it here. And before we jump into the diagram, I would like to clear a few technical concepts, which is nothing but these three reactions: peritectic, eutectic and eutectoid reactions. So these are very important reactions what we see in the iron carbide diagram. So when I talk about a peritectic reaction, in this reaction we have a mixture of a solid and a liquid phase, and at a particular composition and temperature it forms another solid phase individually. For example, if you see this figure in here, we have a combination of a liquid and a solid phase, and at this point, at a particular composition and temperature, we're getting a new kind of solid solely existing. So whenever we have a liquid and a solid phase forming another solid phase completely different and completely independent, we call it as a peritectic reaction. Coming to a eutectic reaction, it involves three phases, wherein a liquid, on cooling at a particular composition, we have two different solid phases coming out of it. So here we have a liquid phase. When it is subjected to cooling at a particular composition, we have our two different solid phases. So this is a eutectic reaction. A eutectoid reaction is something similar, but instead of a liquid phase, we are substituting it with a solid phase. So when a solid at a particular composition, when subjected to cooling, it would give us an other solid phases, and this is vice versa. That is, if you can see two different solid phases at a particular temperature and concentration, they give out a third solid phase altogether. So these are the three reactions which I would like you to get familiarized with before jumping into the iron-iron carbide diagram. So this is the iron-iron carbide diagram. On the x-axis, you have the composition of carbon, and on the y-axis, you have the temperature in degrees Celsius. Now, one thing what we need to know is that any alloy, whenever it has a carbon percentage less than 2% of iron, 2% of carbon, it's called steel. And an iron alloy having carbon percentage greater than 2% and ranging just less than 6.67%, it's called cast iron. So whenever the carbon composition is less than 2%, it's steel, and whenever it's greater than 2% and less than 6.67%, it's a cast iron. So this is something what we need to know. Now, if I have a look at the diagram, there are mainly three important points. This point, which is the peritectic point, this point, which is the eutectic point, and this point, which is the eutectoid point. So let's take it from the top. So post 1600 degrees Celsius, all what you have is liquid, that is the iron is in its molten state, and here you can see it's up till here at 1200 degrees Celsius, the reason being the composition of carbon. So the first top half of the top portion of the diagram, what you see here is iron in its molten state. Now let's have a look at this thing, this reaction, this point, a combination of curves what you see here indicate the peritectic reaction. Now let's have a zoomed in view of this, which brings us here. So this is exactly the liquid phase what I've represented here. And here what you see is the delta iron. Delta iron exists in purely solid form up till 0.10% of carbon. So delta iron exists in purely solid form up to 0.01% carbon, and here you have a mixture of liquid and the delta iron. As I told you, a peritectic reaction occurs when a liquid and a solid form completely give you a new version of a solid, right? So here a liquid and a solid form give you a new version, which is nothing but austenite in here, which I've also represented using gamma. So this particularly occurs at 0.18% of carbon. So having a brief overview again, the delta iron exists in solid phase up to 0.10% of carbon, and post that you've got a mixture of molten state of iron and delta iron, and typically at 0.18% of carbon you have your gamma phase, that is the austenite. So again, this is the phase. Different phases what are represented here are given by the 1-to-1 rule, which is something which is already prescribed, and you can have a look at it later. And this region, the region under the NMP line, represents another region where you have when you're a delta iron and austenite. So at this point, wherein the liquid and the delta iron given a solely independent solid structure is called solid phase, is called as the austenite phase, and this point where it occurs is called as the peritectic reaction or the peritectic point. Now we've completed this region up till now. Coming up to the eutectic region, as I told you, a eutectic reaction occurs when a liquid solely breaks into or solely results in formation of two different solid phases. Here, iron in its molten state is giving you austenite and cementite. Here, I forgot to tell you, this is the cementite phase. So, liquid is giving you austenite and cementite, and hence we call this as the eutectic reaction. A liquid is splitting into two different solids, and this typically occurs at 1147 degrees Celsius and 4.3% of carbon composition. So you just need to remember the temperature and composition where this occurs as well, right? Now coming to the eutectoid point or the eutectoid reaction, as I told you earlier, eutectoid reaction occurs when a solid splits into two independent solids or vice versa. So here In eutectoid reaction, we see austenite splitting into ferrite and pearlite and cementite and pearlite. So this typically occurs at 727 degrees and 0.8% of carbon composition. One thing what we need to note is that in real life applications, we cannot see austenite very common, because when it comes to room temperatures, which is below 600 obviously, uh, austenite is not to be seen, because if you look at the graph, austenite would change into any of these ferrite or perlite or cementite or perlite once it hits 727 degrees Celsius and goes below it. So austenite is not very common to see in your real life applications. One more thing what we need to note is that in the eutectoid reaction, what we're seeing up till this half, the region before 0.8 percentage of carbon composition gives you your hypoeutectoid steel, and between 0.8 and 2 you have your hypereutectoid steels. Okay, and similarly for eutectic reactions, somewhere between 2 and 4.3 you have your hypoeutectic compositions, hypoeutectic phase, and from 4.3 to 6.67 you have your hypereutectic phase. So this is a brief overview as to what an iron carbide diagram is. Thank you.